Morning, everyone. Sign in the page. Sign, right? All right. Do you have any questions about previous lectures related to vectors or any applications? I also published some of the videos. I'm still working on the last one. I published first homework. So you should be able to submit it probably within kind of 2 weeks. So homework will probably take you some time. My point with all of the homeworks is not to fail you, because some of the questions might look unsolvable. That's fine. It's just about the way you solve it. This is what's important, because in this is a graduate course. I'm not looking for correct answers or correct numbers or your ability to calculate things. This is not about calculation. Computers will calculate for you. It's all about way of thinking. And I think that this type of skill is more essential, especially for graduate studies, where you have particular ways of thinking about problems. So solving kind of puzzle problems, something that requires thinking and not just pure calculation and putting numbers into formulas. All right. So if you have any questions, you can ask questions. Regarding grades, some of you might be concerned about what grade I will get if I fail, or what kind of problems I might have if I'm not submitting it in the right way. You shouldn't worry about that part, because again, this is graduate course. It's not about really grades. From my perspective, if you worked on that, if you invested something in that, you tried your best, you get only A and B grades. You cannot get anything less than that. It's not about, again, having correct answers, and so not really multiple choice type of questions. So it's not quizzing you on any kind. It's more understanding and work questions. So don't worry about the grades part, right? It's completely fine to, if all students will get A grade in that course, fine with me, right? The only way you can really fail is not to submit things, not to participate. It's not to come to class, not to learn. All right. So if you don't learn, obviously I cannot give you A. But this is, I guess, obvious. Okay. Any questions? Yes.
Seems that we need to find a scanning machine to scan our assignment.
Mobile phone is fine. I mean,
Take
Cam
a
Scanner. Do you know that app, Cam Scanner, or some other app which is just scanning your photo, scanning your page? If you page on the table, you're taking photos with your mobile phone, and then you just submit it as PDF or doc file. So you can easily do that. Just make sure that it's readable.
Okay.
Otherwise, it's like difficult to evaluate.
Yeah.
Readable, right? Any other questions? So today we'll be working with matrices and linear equations, system of linear equations. And as usual, for other courses, I will go a little bit more into theory before we get to algorithms and applications. At the end, we will see some applications of that, and linear system of equations have also different applications in practice and engineering especially. But we will start with the basic linear algebra just to brush up your information on linear algebra in general. Okay. So matrix, practically speaking, is just a rectangular table or array of numbers. And this table will be like m by m rows by n columns. You have just a bunch of numbers. This is what we call matrix. Sometimes people put it in rectangular brackets, sometimes they put it in round brackets. You have all kinds of notation. And also, these numbers inside the matrix are called elements, similar to vectors. So we will call them elements of a matrix. Now, a matrix has dimensions. The vector has dimension of n by 1, so n elements and 1 width. And matrices have dimension which is m by n. And this is natural thing to define for matrices. So pay attention that we can mathematically write that way, which is A belongs to a set of all real number tables, and tables are m by n. Okay, so that's one way to write it down. And it could be C, for example. It could be not only real numbers, it could be complex numbers. or it could be integer numbers, or it could be any other sets that we discussed before. Yes, you can use other symbols, but typically we'll be using R or C. These are most typical, like real numbers or complex numbers. They cover more or less everything we need. Or you can just write that A has dimensions m by n, and you write that as subscript to the matrix, which is saying m times n. This will mean that you have m rows and n columns. So pay attention, if you know Python, this is misleading because in Python, first dimension is actually not rows, it's columns. But in MATLAB, it's columns, and in linear algebra, it's columns. Okay, so first dimension is always rows. Okay, second dimension is columns. This is how we need to remember it, all right? So if you want to write matrix as just a bunch of elements, you can write that also in this parentheses, in these brackets, round ones or curly ones. And again, first index will be the location of that number row-wise, and second number j will be column-wise location. So A of ij is row I, column j. Any questions so far? This is how we define it. You need just to remember it, unfortunately. A lot of things to remember. Matrices are equal, similarly to vectors, if all of their elements and dimensions are equal. Right, so both matrices should be having same dimensions and same elements, and then they are equal. And practically, if you have all kind of variables inside the elements of the matrix, it's like solving m times n equations. This is what two matrices equal means. Like if A equals to B, and you have some elements which are variables in A or B, then it's practically comparing element by element. So have m times m equations. We'll talk a little bit about special matrices, which we'll use a lot. And these matrices are diagonal matrices. Diagonal matrices are all zero except the main diagonal, which is going from left top to bottom right corner. This is main diagonal. And this will look like that. So you'll have some elements here, which also could be zero, by the way. So any of these numbers also could be zero. But so zero matrix is also diagonal matrix in a sense. Okay, we will not call it diagonal because it's zero, but it is by that definition. All right, but you can have any elements here and zeros everywhere else. All right, and you will also write that as diag all these diagonal elements. And this is a diagonal vector of diagonal elements. Now, typically we will ignore all of the blocks of zero. So if there is zero in particular place or block of zeros in particular place in matrix, we can just ignore it. We will not write anything. It will be like empty space in matrix. So empty space in matrix, it just means it's zeros everywhere, right? So you can write the same matrix just by removing all of the zeros and all these dots, everything. Okay, it will be just main diagonal numbers. Everything else is just empty, nothing in there. Okay, same thing. Just for simplicity of not to make it messy. All right. So in particular, we are interested in matrix which is called identity matrix, and this is matrix with all of the ones on the main diagonal and zeros everywhere else. And this matrix is very important because multiplication by that matrix is not changing another matrix. Like if you multiply A by I, or I by A, it's still A. All right, and this matrix is square matrix. We also can define that using Kronecker delta, which means delta ij, again, row I, column j. And this is defined as 1 if I equals to j, which is on the main diagonal. This is all of these middle numbers, and 0 otherwise. Now, why I'm bringing that example, not because you actually need to be computing anything with that Kronecker delta at that time. It's just in signals and systems, we use Kronecker delta a lot. If you took that course on signals and systems, you have delta, discrete time delta in time, which is one-dimensional delta. So this delta equals to 1 at time 0 and 0 otherwise. But this is two-dimensional Kronecker delta, which is equal to 1 only when both dimensions are equal, both indices are equal, right? So just to give you some connection to other areas. Okay, and also pay attention to something very important, that this works, the rule that I told you that I times any matrix is that matrix. It works not only for square matrices, it works also for rectangular matrices. where number of rows is not equal to number of columns. All right, so let's say you have some matrix M by N, and M is not equal to N. The only thing that you need to change here is that the dimensions of I matrix will be different if you multiply from the right or multiplying from the left. And we will talk about multiplication of matrices later. This is just to show you that these are completely two different matrices, different sizes. If N is not equal to M, these two matrices might be very different. Size is different, all right? But no matter what, if you multiply A by I from left or right, you always will get A, regardless, even if A is rectangular. So this works. Any questions? Okay, another type of popular matrix is triangular matrices. And triangular matrices, you can have lower triangular matrix where all the numbers are below the main diagonal and main diagonal, and everything above the main diagonal zeros. Okay, so upper triangle practically is zero in that matrix, as you can see here as the upper part. And we typically call it L matrix. Okay, lower triangular matrix. So again, as I said before about diagonal matrices, any of these elements A might be also zero or not zero, right? So main diagonal also could be zero. It's still lower triangular if main diagonal is zero, or any of these elements like A and 1 might be zero, or any other number could be zero, right? It's still triangular as long as the upper triangle all zeros, okay? So same thing for upper triangular matrix where numbers are in the upper triangle and lower triangle is zeros. Okay, so these are, we will use them later. Notation comment that U is frequently denoted by R. And then you understand L and R as left and right. So it's like left triangular, right triangular. And again, you can think about that as left and right or upper and lower. It depends on how you look at that matrix, okay? So left triangular means that all the numbers are mostly on the left of the matrix. And right triangular means that most of the numbers on the right of the matrix. Kind of easier to remember, I guess, maybe L and R as instead of low and upper, like lower and upper, think about it as left and right. Okay, so you have two different decompositions that we will talk about in this lecture. One of them is called LU, which is lower and upper decomposition. So you can decompose any matrix into multiplication of lower triangular and upper triangular matrix. But then you have another decomposition which is called QR decomposition of matrices. And R is practically U. So you can call it QU, but it doesn't sound good, so they call it QR decomposition, right? But the meaning of R is practically U. So you need to be aware of that notation that people are using two different letters for the same thing. Q is orthogonal matrix. We will talk about that later. And R is just U matrix, okay? Upper triangular.
Question.
Yes.
So between the left and then the right triangular matrix, what is the main difference? Is it?
So it's like the upper matrix and lower matrix here in that slide. So left and right means that most of the numbers are on the left, which is that L matrix at the top. And upper or right matrix is when most of the numbers are on the right of the matrix. Like it's heavier on the right side. Okay, with numbers. And this is U matrix or R matrix, whatever you call it. Two different names for the same thing. And again, I'm talking about that and giving you maybe too much information about that, that when you read some literature about that, you just will be aware, like what is R, where it comes from, like why they define it that way. It's just notation issues, okay? Different people define different things in different ways. So I'm giving you all the possibilities. Transpose of the matrix very similar to transpose of the vectors. You're just switching between rows and columns. So in matrices sense, you're just flipping that on the main diagonal like that. Okay, so this is transpose. You're flipping the matrix on the main diagonal, which means you're flipping something which was rows. So if you kind of counting numbers by rows, you go like first row, second row, and writing all of these numbers. Now you just start writing same numbers, but as columns, this will be transpose of that matrix. Okay, and it works for rectangular matrices, for square matrices, for any kind of matrices. And here we have two examples how you can kind of flip the transpose. Now in MATLAB, you will use dot prime type of command. So you'll take matrix dot prime, this will be transposed as a matrix. Or you can write the entire command, which is transpose of A. And pay attention that probably 99% of people who are using MATLAB, or many other tools actually, which have that kind of computational commands, use just prime. They say like A prime. Including myself, I'm always using A prime instead of dot prime. So what is the difference between dot prime and A prime? Well, this is a very tricky question actually, because in MATLAB, similar to other languages, regular prime is conjugate transpose, Hermitian transpose. It's also called Hermitian transpose of a matrix, which means if the matrix is real, it's still like regular transpose. If all of the numbers in the matrix are real, you're just transposing the matrix. This is a regular prime. But if numbers are complex numbers, then what happens is first you're making conjugate of all of these numbers, which means instead of A plus BI, you get A minus BI. So you're kind of inverting the sign of all of the imaginary parts and only then doing transpose. All right, so for complex matrices, it will not be transposed. For real matrices, it's still transposed, so it's fine. That's why most people just use regular things because they do not use complex matrices. They don't care. All right, addition, subtraction, same like with vectors, element by element. You're adding numbers, subtracting numbers, element by element. Same thing with multiplication by a scalar. You're just multiplying every element by that scalar, by that constant, and scaling the entire matrix, similar to vectors. But this part is a little bit more interesting, how you multiply matrix by a vector and what it means. If you multiply vectors, and vectors will be on the right and matrix will be on the left, first of all, dimensions need to match, which means that number of columns in matrix A should match the length of the vector that you multiply by, vector x. All right? So you have two ways to do that multiplication. Most of the courses teaching you only one way to do that. But second way is actually more useful to understand like what it means to do multiplication of matrix by a vector. So typical way of all linear algebra courses is to say, well, you're taking first element in the first row, multiplying by the first element of the vector x, plus second one by second one, plus third one by third one, and so on. So it's practically dot product of row in matrix A by that vector x. So taking each row dot product with vector x. And then you get that entire first row of the answer, which will be only one number, okay? It will be dot product of the first row with vector x, dot product of second row with vector x will be second number in the vector answer vector. We'll call it b typically, because it's like ax equals to b vector. And so on, so like you're taking each row dot product with that vector, you get the number. So this is practically explicitly written thing for dot products here. Okay, so this is how people typically learn to multiply rows by columns. And same thing with matrices, by the way. People try to do like rows by columns, and multiplication of two matrices will be element ij will be row I times column j in the second matrix. This is like dot product between rows and columns. But the other way of multiplying matrices is more convenient to interpret what it actually means. Because you can think about that as written here at the bottom. This is the same thing. It's all equal. So it's x1, which is first element of that vector x, times the first column of the matrix A, plus second element times the second column. And again, it's a scalar by vector, so you know how to do that. Just scaling that vector. And so on until you get to the last column, you will get exactly the same thing. So what is the meaning of that? Practically, if you think about vector x as vector of weights, like weight, it's weighted sum of columns of A. You're giving each column particular importance, how important that is in your overall thing is, and then you're doing weighted average. And especially that would be important if sum of the x's will be 1. So if sum of the x's will be 1, it will be percentage-wise weight to each of the columns because it will add up to 1, right? Or 100%. You can do like sum of vector x 100, so it will be in percent. So each column will have particular percent, how much percent you give it, okay? And then you'll have that weighted average of percentages of each column. So this in engineering used very frequently, especially in machine learning and other algorithm development things, because you want to stack together multiple data vectors of some kind, and you'll get some big matrix of some values, features of some kind. And then you want to value each feature, how important that feature is. So you can give it particular weight. You can say like, well, this feature is, I don't care about that feature, but I care about some other feature. So you can weight them using just basic matrix and vector multiplication, right? So you can think about multiplication of matrix by a vector as weighted sum of columns of matrix A, right? Any questions on that?
Well, the answer is a vector?
Is the vector, yes.
Vector as well.
Mhm. So that vector will be like length m. So if A is matrix m by n, and x has to be n because inner indices should be same, the answer will be of size m, right? And what is geometric meaning of the transformation? You have additional meaning, at least in 2 and 3 dimensions, for multiplication of matrix by a vector. So let's take some example. Let's say you have matrix A, which is 0, 3, 2, 1, as you can see here, and you multiply it by vector 2 and 1, okay? As I said, you just scale in the first column, then you scale in the second column, then you add in, and you get in some coordinates, and you have that parallelogram rule where you add in 2 vectors, so you're scaling one of them by 2, you're scaling second one by 1, which is not changing it, obviously, and then you just adding them together, and you get that point 3.5. But try to think about something much simpler than that right now. Try to think about identity matrix, which is like just 1 and 1 on the main diagonal, and zeros on the non-main diagonal, okay? So you can think about that as taking coordinate 0, 1, which is that axis that you have like y-axis, right? And you have 1, 0, which is x-axis. So first column will be practically z-axis, right? Coordinates on z-axis, and it will be like 1. And second one, which is 0, 1, it will be 0, 1. So it will be going into j direction, okay, complex direction. So these are definitions of system of coordinates, right? So you can think about that in 2 dimensions, that identity matrix identifies your classical rectangular system of coordinates, okay? And these are the coordinates in that system, which is 0, 1, 1, 0, and 0, 1, okay? And now you're making weighted sum of these 2 columns. So you practically write in that vector in that system of coordinates. So in that system of coordinates, that vector will be same vector, okay, not changing. But what if you changing one of the axes and giving it some angle, or both of them giving it some angle? So you give one vector looking that way, and it's unity vector, another vector looking some other way, and it's also unity vector, and they might have some angle between them, which might not be 90 degrees, like this too, okay? So one vector looking that way, one vector looking that way, so it's like that kind of, not curvilinear, but non-rectangular system of coordinates. What is the coordinate of that vector in that system of coordinates? This is the question. Now you have the entire thing was kind of squeezed like that, okay? So obviously you'll have some different system of coordinates and different coordinates for any vector you want to write in that system of coordinates. So that multiplication will be exactly this coordinates in that system of coordinates, okay, new system of coordinates. So practically you can think also about multiplication of matrix by a vector as changing system of coordinates, all right? You just squeezing coordinates somehow, scaling them somehow, rotating them somehow, doing some transformation on them. So it's transforming that into different system of coordinates. If all of the columns of matrix A are unit vectors, okay? So they will give you the direction and not size. They will not change the scale of the vector, but they change only direction, all right? So this is other way of looking at multiplication of matrices and vectors. Now, In that particular example, you can span entire space, which means that practically with these two columns, you can write any coordinates anywhere in the space. It will be different from rectangular coordinate, but it will be some pair of numbers, right? So resulting pair could be anywhere in space. We can cover the entire space with points if you choose particular weights in the vector x. So by choosing different numbers in vector x, you can practically receive any point in a rectangular system of coordinates. Now, when that would be not true? When you cannot do that. When you cannot cover the entire space in that like two-dimensional case.
When one is a multiple of the other, when one column is a
Right. So if two vectors are collinear, which means they are in the same direction, you're not spanning the entire system of coordinates. You're kind of squeezing the system of coordinates into one dimension. And then all of the points will be only on that line because you can get something proportional to the first one plus proportional to the second one, but both looking in the same direction. So sum will be also proportional to each one of them. So they are collinear, they are looking in the same direction, so it's you cannot span the space with that type of vectors. So you need to be very careful that your vectors are not proportional. It's not like 1, 2, and 2, 4. Then you cannot do that. Okay. So here's matrix multiplication. As I said, you're just doing dot product between row I and column J in the second matrix. And then you get element ij in the multiplication matrix. Dimensions need to fit together, otherwise you cannot do multiplication of the matrices. So inner dimension, let's say you have matrix of M1 by N1, another matrix M2 by M2. So N1 must be equal to M2 to multiplication to be even defined for matrices. Otherwise it's undefined. And the result will be M1 by M2. So external ones are resulting dimensions. Internal ones must be equal, whatever they are, okay, to do multiplication. And this is a mathematical formula for the element ij. As you can see, you multiply and k should be equal here inside from 1 to n1. And I and j are running indices here. So this is how you compute the actual multiplication. This is just example. If you don't remember, just try it by hand to solve it to get that answer. I will not do that. It's just basic linear algebra. Any questions so far? And I understand that we are jumping kind of from topic to topic because I'm trying to overview different topics and I'm not getting into depth into any of these topics. If you don't remember, just try a few exercises to understand that better. Okay, these are just rules. Important properties of the matrices. You have tons of them. You don't need to remember all of them. Some of them more important than some others. Okay, some of them are easier to remember. Some of them not too easy to remember, but also important. Okay, so let's go through some of them. First one is the most important because this is where most people are doing most of the mistakes. They switch in the order of multiplication in matrices. You just cannot do that. Sometimes it does work, but rarely. Like in majority of cases, AB is not equal to BA. And sometimes it's not even defined for one of them, okay, or both of them. Sometimes the dimensions do not match to switch the order. Also, people have troubles multiplying from left versus multiplying from right, and they don't see the difference. There is huge difference in matrices. It depends if you multiply by matrix from the left or matrix from the right, you get completely different result, okay? Because to simplify something, you always multiply both sides by the same thing, and you can't do that. You can multiply both sides of equation, matrix equation, by the same matrix, for example, from left or from right, but do not switch them. Like left side is multiplied from the left, right side no, it will not work. It's not correct. You need always to keep the same side, okay, when you multiply. And we will see some examples of that. So, and this is practically simple example that you multiply two matrices, and then you switch the direction of two matrices, you switch the order, and you get completely different matrix, not even similar. Nothing in common, okay, not even a single element. All right, so simple rules are that you can switch the addition or subtraction, so you can add here like plus negative a if things of that kind. So all of the other rules are kind of similar to regular algebra. except that AB is not equal BA, right? So this is distributive law also works. So A times C plus B times C, this is still true. But pay attention that this one is different from this one. So it depends if you multiply by C from the right or you multiply by C from the left. Different result. So they are not equal between them, but this still will be true. And as you can see, C stays from the left. And here C stays from the right. So you need to be consistent in how you apply it. This is a distributive law. And again, multiplying by I is not changing anything. Multiplying by 0, any matrix will give you 0 matrix, not necessarily scalar. Transpose of transpose, when you're flipping it back and forth, you get back the same thing. Transpose of the sum will be sum of the transposes. But transpose of the multiplication will switch the order of matrices, which is interesting thing to remember. Okay, this is important. That when you're doing AB multiplication transpose on the multiplication, you need to switch order of A and B to separate the transpose on them. So it's B transpose, A transpose. This is important to remember that. Now scalar, there's associativity. You can associate it with any of the matrices. That's fine. Similar to regular algebra. Just don't change the order of A and B. Okay. This transpose, scalar transpose is scalar itself, so it doesn't matter. You can take it out of the parentheses. So these are kind of basic rules. Any questions on that? Okay, another kind of matrix multiplication which is very popular in programming. Element by element. If both matrices are same dimension, you can multiply them element by element, and it's called Adamar transform. Jacques Adamar developed that for completely different things, but now in computing you have a lot of that type of multiplications. And interestingly, all of the rules for these matrices are very similar to regular algebra. Okay, if you multiply them element by element, you get all the same rules, and you can switch the order, obviously, and you can do distributive law, associative law, all of that stuff to take constants outside of that and say multiplication by zero will give you zero. Which are, most of them are kind of obvious because you're doing that element by element. So it's like each element satisfies regular algebra. So the rules should satisfy. Symbol that multiplication symbol. Okay, multiple different ways to do that. Another term which is called trace is sum of all of the main diagonal elements. So summing all of the main diagonal elements, you get trace of the matrix. Also, very important thing in multiple different domains. And you have all kinds of rules for trace. Trace of sum is sum of traces. Trace of AB equals to trace of BA, which is interesting. So AB is not equal to BA. But if both of them are defined, which means dimensions match, they clearly have different dimensions if they're rectangular. Okay? They are different, but trace will be the same, regardless what these matrices are. Trace of transpose will be trace of the matrix, which is obvious because you kind of flipping that on the main diagonal, you're not even changing main diagonal. So obviously the trace will be the same. Trace is also kind of linear type of operator, which you can take constant out of that operator. So if you multiply something by constant, trace will be also multiplied by the same constant. So the sum also will be multiplied by the same constant for obvious reasons. And in MATLAB, it's just function trace. Any questions on trace? We'll do some example. And in that example, we want to solve. I will write this matrix in the board. Some of that stuff works. So a matrix is given by 1, 2, 3, -4, -5, 0. Matrix B is given by 1, 2, -3, -4, 0, 5. And you want to compute AB, BA, trace, AB and trace BA. These two things. All right, so let's multiply it. First of all, we need to identify dimensions if we even can do that. So what are the dimensions of A matrix?
2 by 3.
So it's 2 by 3. So this matrix is 2 times 3. What is the second one?
3 by 2.
3 by 2.
3 by 2. So inner dimensions fit, so I can multiply A by B. Okay, so what is A by B? Will be, yeah, 1, 2, 3, minus 4, minus 5, 0, times that matrix, which is 1, 2, minus 3, minus 4, 0, 5. So you get matrix, which will be what dimensions?
By 2.
2 by 2. Those are external numbers. Okay, that will be 4 elements. First part will be taking that row multiplying by that column will be 1 plus 2 times minus 3 minus 6 plus 3 times 0. That's it, right? The second element will be first row, second column. So it's 1 times 2 is 2. 2 times negative 4 is minus 8. 3 times 5 is 15. Okay. This element will be minus 4 times 1, it's minus 4. Minus 5 times minus 3, it's plus 15. And 0 times 0 is 0. Right? And the last one is minus 4 times 2. It's minus 8. Minus 5 times minus 4, it's plus 20. And 0 times 5 is 0. So that's it. So you'll get 1 minus 6 is minus 5. 2 minus 8 is minus 6 plus 15, 9. Here's 11 and 12. Okay, same thing with BA. So BA will be 1, 2, minus 3, minus 4, 0, 5, times 1, 2, 3, minus 4, minus 5, 0. What are the dimensions of that matrix? 3 by 3. Then you get here 1 minus 8, 2 minus 10. I will just copy the numbers. You can verify by yourself. Now you have only pairs of numbers because it's like 1 times 1 plus 2 times minus 4, so on. So we'll get all these numbers. And the result will be minus 7, minus 8, 3, 13, 14, negative 9, minus 20, 25, and 0. Okay. And now we compute trace of that. It will be minus 5 and 12. So it will be sum of minus 5 and 12. Minus 5 is 7. Now we need to add these three numbers. So it will be negative 7 plus 14 plus 0. So obviously it will be also 7. So math works. Congratulations. Same number. So trace of AB equals to BA, but obviously AB is not equal to BA, right? Any questions on that? This is my claim. Now we want to divide matrices. We multiplied matrices, now we want to divide matrices. Unfortunately, you cannot do that. But you can do something else. You can invert matrices. You cannot divide them, but you can find matrix which will be like division, like opposite from multiplication in a sense, if the matrix is invertible. And we will define B as inverse of the matrix A if AB equals BA and equals I. So we've got something which will multiply from left or right by that matrix B. And then you will get identity matrix. Right? This is how you define the inverse. And we will use also symbol A inverse 1, like to the power of -1, to show that inverse matrix. Okay, this will be that matrix B. And this matrix is also called non-singular, because non-invertible matrices are called singular, which means you cannot invert them, they are singular. And non-singular means invertible. So how do you actually do that? We will not work much on that. It's more complicated than it needs to be. We will see some examples of that. But you need to remember only 2 by 2 matrix inversion. Okay, because we will use that in examples, so it will be easier for you just to remember how you invert generic matrix with elements A, B, C, D, and you're making inverse matrix of that. So this is what you do. You divide by determinant, and this thing is called determinant. Again, we'll have an entire lecture on determinants and the relation to practice. But AD minus BC is determinant. So you're taking A times D minus B times C, okay, and you're dividing by that number. Which also means that if this number is 0, the matrix is not invertible. If determinant of the matrix is 0, the matrix is singular, not invertible. And then you switch main diagonal numbers and making negative to the non-main diagonal numbers, which means you switch between A and D, and you're making minus C and minus B in these corners. This is how you do that. So inverse of matrix A, B, C, D, you're dividing by determinant, switching main diagonal, putting minus sign in other corners. That's it. That's how you invert 2 by 2 matrix. 3 by 3 is more technical. You have some formulas for that, how to do that. Maybe we'll go through some of them, but not sure if it is essential because computers are doing that for you. Okay, we'll see algorithm how you can do that, but we will not do that by hand. Okay, so in MATLAB, you're just writing power -1. This is inverse of the matrix or inv command, and this will do inverse matrix A, if it is invertible. So it's very important to remember that when you have some matrix equations, and multiple different types of matrix equations are very popular in fields like control theory, and also in power generation, in machine learning, you have multiple matrix equations. You cannot cancel matrices. You can, like if matrix A multiplies from the left, both sides of the equation, you cannot just cancel it. Because first of all, this matrix might be not invertible. So you cannot divide by that matrix, okay? Because cancellation is like division by in the meaning, okay? So you cannot do that. First of all, you need to be sure that it is invertible. And then you can multiply from the left by A inverse, and then it will disappear from both sides. Okay, so this is how you handle it. So here's one simple example that you want to solve, for example, that equation and to find relation between B and C matrices, okay, in that equation. So in regular algebra, what you would do, you would just cancel A, cancel B on that side, and then you'll get, practically speaking, B plus C equals to 0, right? That's what you would get in regular numbers. But in matrices, you cannot do that. The result will be the same, but you just cannot do it that way. So here's how you practically officially need to do that. The steps that you need to take to cancel out all these elements. So if A and B, if A inverse exists, okay, this is first step. Let's say it exists, all right? So you can multiply from the left here by A inverse, and here by A inverse, and here by A inverse. So in A inverse times zero matrix, and pay attention, it's not number, it's matrix of zeros, okay, of appropriate dimensions. So this 0 times A inverse will be 0. Like everything times 0 is 0. Matrix, 0 matrix, not 0 number. Okay? A inverse A will be I, right? Because this is how it's defined, inverse, all right? Here A inverse A also will be I. So you'll be left with B squared plus CB equals 0. This is what you get here, right? So multiplying on both sides, you get B squared plus CB equals to 0. Now, and multiply by B from the right, B inverse from the right, to cancel that square here, and B squared is just B times B. So B square will be cancelled, and B will be cancelled if B is invertible. So it must be invertible in the first place. So this must be conditioned to solve that equation in the first place. Otherwise, you cannot even solve that equation. So multiply by B inverse here, B inverse here. B squared times B inverse will be just B. And here B times B inverse will be just I. And I times C will be C. And then finally you'll get B plus C equals to 0. Okay. Which is kind of a long process, but this is how you need to go with matrices to stay on the careful side. Okay, unless you actually see it, like how you do that in your mind. Like start with all the steps first, and then get to the right thing. Orthogonal matrices are also a very important part of linear algebra. And this is because this matrix is practically defining new systems of coordinates. Orthogonal matrices mean that all of the columns are orthogonal in that matrix, which means dot product between pairwise columns will always be 0 or 1 if you're doing that. First column to first column will be 1, but first column to any other column will be 0. So they are orthogonal, perpendicular to each one of the other columns. And interesting property of these matrices is that their A transpose is their own inverse, which means this is what it says here practically. It says that A transpose A equals A transpose equals I, which means that A transpose is the inverse of that matrix. Very simple to compute A inverse, right? It's like super easy thing. And this is why most of the integral transforms represented by matrices and other things converted into this orthogonal matrices, like Fourier transform, for example. We will see some examples of that. Because it's very easy to compute inverse of that transform just by transposing the matrix. And you get inverse transform compared to forward transform. You have Fourier transform, for example, and inverse Fourier transform. You get inverse Fourier transform, just transposing the matrix, and you get matrix for inverse. Okay, very simple. Now, this matrix is called also orthonormal if it is orthogonal, and all the vectors have norm 1. So it's all unit vectors, all the columns. Okay, this is called orthonormal vectors. Okay, how we solve system of linear equations? Yes.
Must it be a square matrix?
It has to be square matrix, yes. Otherwise, you will not be able to do all this inverse stuff. So inverse is only for square matrices. You cannot invert rectangular matrix. But good question. Solving system of linear equations. This is where linear algebra courses typically stuck like for 5 weeks. We will not do that. We don't need it because we will just write algorithms for how to solve system of linear equations. I will mention methods that people are using for solving linear equations, multiple different methods, and you've probably seen maybe 1 or 2 of them before. But we will concentrate on how you write algorithm to solve system of linear equations and what it all means. We will do this will be probably last example by hand that we will do in class for systems of linear equations, just to solve them, to see how you cancel different things, how you write one thing as a function of another thing. But practically speaking, in linear algebra, it's very simple. You just need to find inverse of a matrix. And frankly, I think, again, I'm not a historian of any kind, but it seems that linear algebra and matrices were defined, as I mentioned already before, like a few lectures back, because of this linear system of equations in a very specific way. And multiplication of matrices by vectors were defined in that particular way because of this writing. So you want that thing to be written as AX times AX equals to B, okay, in matrix notation. That entire system of things, and you have tons of numbers here, different numbers there, tons of different unknowns here. You want to write that as a shortcut as matrix A of coefficients A times vector of unknowns X equals vector of numbers B, right? All of that system of equations in generic form. And this will look like that. Okay, so this is absolutely equivalent description of that thing. And if you're taking that one as A, X, and B, you can write AX equals to B. So simple to manipulate, right? So if you learn all of the rules manipulation of the matrices, all of them defined for that purpose initially, most likely, to manipulate that type of systems of equations. So all you need to solve that is to make sure that this is invertible. And then you multiply on the left with A inverse, and here A inverse, you get something like that. So A inverse A will give you I times X will give you X. Okay, so X equals A inverse B. That's it. Okay, this is a solution. So all you need is to know how to find that A inverse, practically speaking. And for that you have Gaussian elimination, for that you have all kinds of transforms and all kinds of decompositions. You have tons of different algorithms to do that in fast and efficient way. But Gaussian elimination is the most popular one, probably. So here is one example. You see that you can have that matrix of coefficients 3, 4, 5, minus 7 times vector of unknowns x1, x2 times equals to all of the free coefficients 3 and 0. So you just need inverse of that matrix. So inverse of that matrix, as we've seen, is 1 divided by determinant, which is 3 times negative 7 minus 5 times 4. So this is a bottom part determinant. Okay. Here we switch in 3 and negative 7, switching the order and putting minus here and minus there to invert that matrix. If you remember the rules that I talked about 2 slides ago. So you compute that and you get two numbers, which is x1 and x2. This is how you solve it, okay, for 2x2 system. Just by inverting the matrix. What is the geometric meaning of solution of system of equations for 2 equations? So if you have generic system, you can think about each one of the equations as line in space using coordinates x1 and x2. So one line and another line, if you need them to be solved simultaneously, you're looking for crossing between these 2 lines, which is coordinates of crossing between these 2 lines geometrically, okay? But you can have other kind of things happening. Lines could be parallel or they could coincide. And then you have no solutions, like no crossing at all, or infinite number of solutions if they coincide, right? So the only way that you will have single solution and invertible matrix is when the lines are like that. So they have different angle. They have to have different angle and only then they will cross each other at one point. And they can cross only at one point, obviously. Infinite lines. Any questions on geometrical intuition behind solution of system of equations? At least 2 equations. We will see also 3 equations. It's a little bit more complex because you have planes instead of lines in 3D. But it's very simple geometrically for 2 dimensions. So sometimes you will have something which is called undetermined system. And systems might be having, again, infinite number of solutions or no solutions at all. So they may, like 2 equations might contradict each other, practically speaking. So here's just one example where 2 of these columns are proportional, which means this matrix is not invertible because determinant is 1 times negative 2 minus 2 times negative 1, which is 0. So you cannot divide by 0, so you cannot compute the determinant, division by determinant. So you cannot invert that matrix. This matrix is not invertible. And these are the 2 equations that you get from it, okay? x1 equals to x2 and x1 equals to x2, same equation, practically twice. What do you get from that? You get practically infinite number of solutions here because you can pick any of the x's and other x will be the same. You can have infinite number of solutions, which means that both lines are coincide practically. This is what happens in 3 dimensions. In 3 dimensions, you have more cases. You have 3 different planes. So each equation is a plane in space. So they could be parallel. Some of them might be parallel and some crossing. But the only way to get single solution is when all of them are looking that way, okay? So they have single point of crossing. Then you have single solution, and this is where the matrix becomes invertible and you can actually find it. As you can see, most of the cases are not like that in 3 dimensions or more. So it's relatively rare property in a sense. So only that solution has like single dot where they all cross at one point. But they can cross at multiple points. So you have infinite number of solutions. Here it's also infinite number of solutions, infinite number of solutions. No solutions at all. Okay, again, no solutions, no solutions, no solutions. Like most of the cases, actually no solutions. You have no solutions because they do not cross at one point or even multiple points. It's just completely random slopes. Any questions on the geometric intuition behind what happens is solving systems of equations? Okay, so yes.
So aside the underdetermined equations, I also see an overdetermined.
Yes, we will have probably even a few lectures on overdetermined systems of equations, solving with least squares. How do you do if you have practically no solution, but you still want some solution because no solution because of the all kind of uncertainties, noise, and other things, practical things. So this is like theory of it. In practice, we still want some solutions, even if you don't have any theoretically. So you're looking like for closest solution if you would have solution type of thing.
So the underdetermined has several solutions, and then the overdetermined
It has practically incompatible solutions. So you have no solutions. Like theoretically, you have no solutions numerically. But practically, you are looking for a solution which gives you minimum error if you would modify a little bit your system, right? This is what we are trying to do. Like we try to manipulate the system that it will have solutions, and then how you manipulate it in minimal way, in such a way that you will have some solution. Because again, all of the systems in practice coming from data points. You're measuring something and your measurement is not accurate. So you don't know if this number is precise or not, or accurate or not. You need to do something with that. You're saying, well, I will assume that there is some noise in it. Okay, so it's like plus minus, some tolerance, whatever it is. And I will assume that this tolerance is minimal possible to compute something that I will have solution to that problem. And these are typically least squares type of solutions. And you have even multiple different types of least squares, different algorithms which are helping you to do that. Okay, but just getting back to theory of how you can solve systems of equations in general. So Gaussian elimination, I'm not going through Gaussian elimination and all of that row echelon forms. You have reduced echelon forms, you have all kind of. I will go just through the idea of it. I will not actually do it, and we will not stay for long on that thing. And this is one interesting fact about Gaussian elimination. Gauss has nothing to do with it. Okay, so nicht means no in German. It was known like 1,000 years before Gauss, how to do Gaussian elimination. So it's a misnomer in a sense to call it Gaussian elimination, but everyone calls it Gaussian elimination now. So we'll continue the tradition of calling it the wrong way. Another way is using determinants, Cramer's rule. Again, I think it's like long before Gauss. It was known how to solve systems of equations with determinants. And determinants were invented before linear algebra, which is also an interesting fact in history. That people used determinants before there was matrices. They used just as tables of numbers, that kind of thing. And practically, this rule is very simple. We will talk about that rule when we get to determinants. LU decomposition practically is Gaussian elimination, but with matrices. It's convenient way to solve system of linear equations, converting it into lower diagonal and upper, and not diagonal, triangular and upper triangular matrices. So you put matrix A as multiplication of these two matrices, okay? And as you can imagine, solving system of linear equations with triangular matrices is extremely simple. Why? Because in the corner of triangular matrix, you have single number, everything else is zero. So you have, for example, like A11 times X1 equals number. This is your first equation. It's just equation with one variable and one, like you just dividing B1 by A11. Okay, you get X1. Then you can substitute that X1 into the second, third, and all of the other equations. So all of that left part, like left column, becomes numbers instead of something times X. Okay. So each time you have equation with one variable, you compute for X2 now, then you compute for X3, then you compute for X4, like step by step, like propagating forward row by row from the triangular matrix. So if you have triangular representation of your system of equations, it's super easy to solve it. Okay, just solving it step by step, iteratively, and that's it. Now, LU decomposition allows you to do that. We will see how to do that. You have QR decomposition, as I mentioned already. Again, this is that matrix, which is orthonormal matrix, times upper triangular matrix, which is R, or right matrix, right triangular matrix, okay? And we will see why it is very easy to compute that kind of thing. Again, because of the Q transpose equals to Q inverse. Okay, then it's very easy to manipulate that type of equations. So here's how Gaussian elimination works. All right. So Gaussian elimination is based on a few simple properties of equations, linear equations in that case. First of all, if you switch in any equations, order of equations doesn't matter. Right? If you have system of linear equations and you say that your first equation will be fifth equation, who cares? Doesn't matter. Right? It doesn't matter in which order you put the equations. They still have same solution. Okay. This is number one. Number two, you can replace each equation with this equation minus constant times any other equation. Okay, this is linear property of this linear equation. This is very important property, which means you can add two equations together and replace one of these equations by that equation. You can subtract them, put them instead of that equation. You can do any other linear operation, which is linear combination of these two equations, and you will get still same result, right? So any linear combination could replace any of the equations, practically speaking. And you can also multiply by any constant the entire equation and you will have same solution. Because if you multiply the B part and all of the A part by same constant, like the entire equation, both sides you multiply by the same constant or divide by the same constant, doesn't matter except zero. It's same equation, right? Because you can always cancel that number if you want to. Yes.
Can you read the nomenclature, replacing?
Yes, on that one,
Yes.
that says that if you replace row I with row I minus some constant times row j, some other row, okay, for any alpha, and alpha is just some constant, some scalar constant. So if for any alpha you replace in that row with that thing, it does not change the solution x, okay? So you can manipulate it in multiple different ways. And this is what Gaussian elimination is based on these rules, simple rules. And by these rules, you put in that matrix A here and that vector B here. This is like 4 by 4, but you can do that for any dimension, doesn't matter. So you're expanding your matrix with column B, which is the solution of AX equals to B, right? So this is B, this is A, and then you're eliminating all of these numbers, they become zeros. How you eliminate that? You're just taking that number and subtracting and using it here. Okay, and then you're subtracting from that line, from that row, you're subtracting that row divided by that thing. Okay, so you get practically here zero. So making sure that this coefficient is proportional to that coefficient. So you're doing that coefficient of proportion here, so subtracting it every time. And you're doing that for each row below the pivot number, okay? Again, I'm not going into linear algebra. If you don't remember it, you don't have to remember it. It's just, you have the technique to make from that matrix triangular matrix, practically speaking. Eventually you'll get to something like that by killing all of these terms below the pivot numbers, okay? And then you can easily solve that thing by backward elimination. So you can remove the same thing going upward from the bottom row to the top row. Same process, but going up. Second time, and then you get diagonal matrix times that thing. This is very easy to solve, which means it's just that number times x equals that number. It's the system of n equations where each equation is single variable. That's it. And you don't even need to go through that process. Practically speaking, you can solve it from here again, the way I told you. You're just saying like z coefficient times last x equals last b, right? So you can find the last x. You can substitute that last x here to all of this, okay? And you will get just different numbers, and then you can compute the n minus 1 x, and then n minus 2 x, and so on. So it's just substituting backwards, and you're getting all these numbers back. But again, we are not dealing with that in this course, so it doesn't matter really. Just to remind you that this thing exists, okay? So here's how forward elimination works. Here is one example. Just let's say these are numbers, okay? And these are numbers. And these are unknowns. You want to find x1, 2, 3. So x1 times a11 equals b1. That's it. So you can compute x1 as b1 divided by a11, right? Now you know ax1, so you can put it here, right? So it's a121 times x1, which is that number now, plus a22 times x2, which is still unknown, equals b2, which is a number. So you have that kind of equation. So this is a number, this is number, this is unknown, this is number. Practically equation with one variable x2, which is linear equation. We know how to solve it. This is how you solve it. Okay, all of these are numbers. Now, after you know what x1 is from the previous one, x1 is this thing. Okay, so you replace x1 with that thing here, and you get x2. And so on, and you can go like line by line down. This is the overall formula how you do that. Just divide by ai for I, and this is b minus sum of all of the previously computed values. So you're doing that kind of recursively. This is how that elimination works. So here's the idea how you solve that using LU and QR. This decompositions. You have two types of decompositions. As I said, you can write any matrix A as LU, L times U, lower triangular times upper triangular. And then here's what happens. So AX equals to B. This is our equation that we want to solve, right? So A will be replaced by LU. This is a decomposition that I made for that matrix. But I can reorganize it and put parentheses around UX. Associative law, right, for matrices. It still works, same like algebra. And this is what you get. Because look, what happens here, this is some sort of vector. Unknown vector. Let's call it Y. Okay, some vector that you want to find. And this equation will be L times Y equals B, right? And L is lower triangular matrix. So this is easy to solve, right? It's again the things that we discussed before. Forward elimination, you find solution Y when you have that equation, Ly equals B. So this is my kind of new X. So L, that new X, which is called Y, equals B. I solve it easily by forward elimination, which we discussed here by that formula. Okay, so this is first step. And second step, now I have U times X equals that Y. So Y now is known vector because I computed it already, right? And U is upper triangular matrix, again, very easy to solve by backward elimination, going like from bottom up now, instead of from top to bottom. That's it. So you solve those two triangular systems instead of going through that entire system. Very easy. So this is number one. And number two is QR decomposition. Again, I said the Q matrix is orthogonal matrix, which means Q transpose equals Q inverse in that case. And I decompose matrix A as multiplication of that type of matrix. And I'm not saying how right now, but you can do that. And then I decompose it as that multiplication. So A equals QR practically. So very similar to the left side of things. You say that practically speaking, AX equals to QRX. And then I can redistribute it like that, associative law. Okay, so Rx equals to B. But here is different step from the previous one. Okay, so previously I just said, well, let me solve that part separately. But here I'm saying Q is easy to invert. So why not to multiply two sides by Q transpose? Okay, and this is what I do. I'm multiplying both sides by Q transpose from left and Q transpose from left and B, right? But Q transpose Q is what?
I.
It's I, by definition of that particular specific matrix, okay? It's just nothing. And I times anything is that anything, okay? So this will cancel out. Practically, you'll have Rx equals to Q transpose B. And here is what you get. So Rx equals practically Q inverse B, or Q transpose B, right? So here's the thing, that this equation is very simple to solve because R is U, is like upper triangular matrix. And this is some sort of vector, right? Just numerical vector, some numbers, vector of numbers. Because matrix times vector is vector of the same size. All of the matrices are square matrices in that case. So you just solve regular Qx equals vector type of thing, okay, as before. So solving only one equation, practically, only one system of equations with triangular matrix, very easy thing to do. Okay, so these are like overall ideas how you solve it. We will see more about that a little bit later, but here's how you do that in Matlab. You have LU decomposition, and then you have also QR decomposition, which is QR comment in Matlab. So these are two functions to get these matrices out of matrix A. All right, any questions? Yes.
So this give exact solutions.
Those are exact solutions, yes.
And also you
Only when matrix A is inverted.
so if the matrix is invertible, you can always transform it into
Yes.
either QR or LU.
Other questions? All right, thank you, that's it for today.